To yammering. Yeah, all right. Let's see here. So sorry the others are not here. So I'll begin with a word of prayer. Dear Father, we thank you again for your many blessings, and just pray that you just be with us today, help us to glorify you in what we do, and just understand a little bit more about Riemannian metrics. Lord, in your name I pray, Lord Jesus. Amen. So let's see here. We defined last time the concept of Riemannian geometry. So basically, we have a manifold and a rank 2 tensor field, right? So like G at a point P would be a mapping from like TPM cross TPM to the reals again. And in a nutshell, it's an inner product, right? It's a real inner product on the tangent space at the point. And we suppose that this is a smooth assignment, right? So it's a smooth tensor field on the manifold, right? So we have one of these at each point, and they're assembled in a smooth fashion, and as such, we can define like a variety of different things, right? Like so. See, we just kind of recap. If this is your manifold, if I wanted to say go from a point P to a point Q, I could calculate the distance from P to Q, right? The distance from P to Q, it would be the inf of the I forgot the notation for it. I guess it was length of gamma, something like that. Where if we have gamma as a mapping, let's say from say T1, T2 to M, and gamma of T1 is P and gamma of T2 is Q, right? Then the length of gamma was defined to be the integral, say from T1 to T2 of, basically it's just G sub P of gamma prime of T, gamma prime of T dt. Now, that's not quite it, right? Because that would essentially calculate the length squared, right? So we square root that thing, and so basically that's a formula for the speed of the curve with respect to the metric in some sense. So, classical formula for all this is something like ds squared is equal to the sum over I and j of, like gij, dxi, dxj. Remember, the metric has to be a symmetric tensor and something like that. So if you take the square root of that and you integrate it, that calculates the length, essentially, for a particular curve, and then you just take the infimum over all possible curves. I'm not going to write all the details here. The infimum for all possible curves there gives us the definition for the distance between 2 points, and he's got about 2 pages where he proves that that's an honest-to-goodness distance function in the sense of, a formal metric like you'd study in, functional analysis, or like you're studying in your topology course right now, right? So that's great. And I also mentioned that we can define like an orthonormal frame, and it would be a G orthonormal frame, like G orthonormal frame. So if that were talking about like, EI, usual list of vectors, right? It would have the following property, like essentially G of EI, EJ is just Kronecker delta IJ, right? So it's, in that sense, orthonormal. Now I say G orthonormal because for a given point set, for a given set of points, we might have more than one possible metric. All right, so like for example, let's just take the plane, right? On the one hand, you could talk about G bar. I'm an idiot. G bar. So dx squared plus dy squared is the the Euclidean metric on the plane, right? There are other things, though. There are all kinds of other weird metrics we could put on the plane. Let's see here. One nice construction one nice way to create new metrics from nothing, so to speak, is this pullback construction. So here's basically the idea. I guess I'll do it here for now. If we had another way we could do this is we could think about the plane, maybe I shouldn't use x and y for this construct. I don't know. I don't know. Well, he uses u and v in the notes. In the book, I guess I'll just do that too. I'm chickening out here. U, v. So.
You said we could have more than one metric. Did you mean like you can use different metrics at different times, or like both at the same time?
Well, there's no time for us, but I mean, who wants to live forever anyway? But I'm an idiot. For a given Riemannian, good grief, I can't talk. For a given Riemannian manifold, there is a specific and fixed metric we're talking about. Now, it is an interesting question to ask for a given space. Could you look at different metrics, and perhaps could you look at a parametric family of metrics, and could you like morph from one metric to another? Could you like flow between different choices of metrics? That might be an interesting thing to look at, but I don't think we're looking at that in here. Some of the deeper research in differential geometry, I think, has concerned basically like deforming between one space and another or something like that. That's actually what you're looking into. Homotopy is about that kind of idea, deformation. Okay, so if we parameterize, we can parameterize the upper half of the sphere. All right, so like the upper half of the sphere, let's call it big X. For like, I like to use that for the parameterization, So over here, let's say I've got Z, I've got Y, I've got X as usual, right? And to parameterize the upper half of the sphere, I have X of UV is, well, I can just do UV and then square root of, what do you want the radius of the sphere to be? Let's make it radius 1, all right? So unit sphere, 1 minus u squared minus v squared, right? So if you look at that, that definitely is a patch on the sphere, right? The inverse of x would be a chart on the sphere, part of the sphere anyway. And so if you think of this as being x, this as being y, this as being z, you can easily see that you've got x squared plus y squared plus z squared equal to 1, right? So that's definitely a parameterization of the upper hemisphere there. All right, so great. So at the moment, Jeff, I'm talking about the plane, and I'm trying to figure out how to build a new metric on the plane besides just the Euclidean metric is dx squared plus dy squared. The question is what other metrics could we build on the plane, right? Different metrics give us a different geometry. Like geometry is a question of a set paired with the metric. So I'm going to show you how we can define a different geometry on the plane right now by pulling back the metric on 3 dimensions. So like over here, the 3-dimensional Jabbar, I'm an idiot, is dx squared plus dy squared plus dz squared, right? That's the Euclidean metric on 3-dimensional space, right? So one thing I could do is I could take this, rank 2 tensor covariant tensor field there that's defined in all of R3, right? I can restrict it to the sphere, yeah? And then I can pull it back under this X map, right? I can calculate over here X pull back G bar and see what that gets me. See, that's going to get me a different metric on the UV plane, which of course we could think of as the plane. Maybe it's helpful to not use X and Y, just to see the distinction in the roles between the XY over there and the UV over here, perhaps. So how do we actually calculate the formula for that? I think we should do that. Give me 5 minutes to clean off the middle board. I'm not happy. I'm ahead in the pie face thing right now. I just emailed the organizer to find out if I can buy tickets, because I'd like to see Sprano in the lead. There's the Women of Engineering or something doing some kind of fundraiser where they're going to hit people in the face with a pie. And I volunteered for this thing because I'm an idiot. And they asked me. And I made it contingent upon Sprano participating, and he did. He didn't know I made my participation contingent on his, but he just did. And so I was hoping that Sprano's popularity would serve me well, but I don't know. The number of tickets were pretty low though, so I feel like if this is like a I can buy tickets kind of thing, I feel like I can purchase Dr. Sprano getting hit in the face with a pie as opposed to me.
Either way, don't they get money? They would probably get more money if you did.
Well, yeah, I mean, I'd be willing to spend a little bit of money to not get hit in the face with a pie, especially if it means that Dr. Sprano is going to get hit instead of me. You know?
You should go to all your classes and tell your students if they show that they bought a ticket.
bonus points if they bought a ticket for Sprano.
1 point per ticket.
Nice. Very nice. Very nice. So let's calculate the formula for this here thing, right? So we got the pullback a G bar. So we're talking about X pullback of, if you want me to write it out in detail, it's dx tensor dx, right? Plus dy tensor dy, plus dz tensor dz. And what does that actually mean? What is a pullback? How does that actually work? How it actually works is we simply set x equals to u, y equals to v, and z equal to the square root of 1 minus u squared minus v squared. Yuck. Hey, this is new. Why is this already this is a new marker. Why is it already kind of not cool? Anyway, so of course, the pullback just says substitute the formulas in and work it out, right? That's how it goes. So of course, first we got du squared, or du tensor du. So that becomes du squared. That becomes dv squared. And over here we've got, what's the, over here we'd have let me write out the things symbolically for a second here. So partial z, partial u du, plus partial z, partial v dv squared, in the sense of tensor product. Okay, so that square we need to understand is a tensor square, right? It's just a shorthand for tensor product of that thing with itself. So it's going to have cross terms, I think. Okay, so what is partial z? Partial u, for instance, it is minus 2u over 2 square root 1 minus u squared minus v squared, right? So that's actually just u over, I guess it's u over z if I want to be lazy, right? Agree?
Not minus.
With a minus, thank you. So to save myself writing I think I've got du squared plus dv squared plus, well, minus u du minus v dv over z quantity squared. All right, so that's actually du squared plus dv squared, and get rid of the minus, right? Plus what? Plus like u squared over z squared du squared plus, oh, fine, let me write it out because otherwise it's going to be really weird what I'm doing. I mean, it's still weird enough, but 1 over z squared, and we got u du plus v dv tensor, u du plus v dv. If that makes sense. Even if it doesn't make sense, that's what I'm doing. So, whatever. All right, so what you got here? We got a 1 plus u squared over z squared. That's my du tensor du term. All right. And then I've also got a 1 plus v squared over z squared, dv tensor dv. And then I've got like cross terms, right? Like, let's see here. So like uv over z squared, and there I'm going to have du tensor dv plus dv tensor du. Oh, rats, I've forgotten. What was our definition of like, what was our definition of du dv last time in terms of tensor? Was it 1/2? I think it was 1/2 du tensor dv plus dv tensor du. Of course, we did it with like alpha and beta, but that was the symmetric product of the covectors alpha and beta. All right. So I've got uv, I've got vu, but you see I'm missing the 2. So to rewrite this, I have 1 plus u squared over v squared du squared plus 1 plus v squared over z squared. Oh man, that was a z, my bad. Z squared dv squared, and then this is, I believe, plus 2uv over z squared du dv. If I pull a z squared out of everything, what do I got? I can put a 1 over 1 minus u squared minus v squared, right? I'm going to factor it out of everything. Okay, everything. So when I do that, that makes this have a z squared plus u squared, right? Like this term becomes z squared plus u squared if I factor out the z squared in the denominator. So what is z squared plus u squared? Well, z squared plus u squared is 1 minus u squared minus v squared plus u squared, also known as, 1 minus v squared. So this is going to give me 1 minus v squared du squared plus 1 minus u squared dv squared plus 2uv du dv. Now, that certainly doesn't define a metric on all of the plane, right? So this is going to gives a metric, what? U squared plus v squared, what? Less than. We're going to get into a lot of trouble if we get to u squared plus v squared equal to 1, right?
Yeah.
Yeah, that's bad. So less than 1, that would probably be better. But that is what's called the pullback metric on the plane from, well, it is an example of a pullback metric on the plane, in this case from the sphere. And obviously this is not the Euclidean metric, right? Quite clearly, it's a different metric on the plane. And I believe you could show, once we have the tools, you could show that this gives us a geometry which makes the plane not what's called flat. I believe this would make the plane have positive curvature. I think that's true. I haven't checked it, but I believe my intuition says that that's what should happen. But my intuition could be wrong.
Positive curvature means that, like, if you have parallel lines, they go towards each other.
It's just meaningless words for me at the moment.
Okay.
But yeah, I think so. Okay, so this is one thing we can do. We can talk about the pullback metric. Now, generically speaking, this is not just for surfaces, right? So like, oh, did I ever move? I think I moved. Yeah, I moved. So definition, the pullback metric, if you have, like a smooth function from a manifold M to another manifold N, and, N comma G is Riemannian manifold, right? Then F pullback G is Riemannian metric on M. And again, I'm assuming F is a smooth map. Okay. Well, that's not quite it. The proposition that I should be more careful. We do need to know a little bit more, right? We do need a little bit more than that. So this is proposition 13.9. Proposition 13.9 says that if you've got a smooth map and G is a Riemannian metric on N, it says that F star G is a Riemannian metric. All right. If and only if F is smooth immersion. All right. Now, what does that mean? What's smooth immersion mean?
The rank is injective.
The rank is injective. Right idea. Differential is injective, right? The
rank equals the dimension of the
in this case M. M, right? Yeah.
The differential is injective.
So there's no the kernel of the differential is 0, right? Yeah. Okay, so the next example actually is another example of something called a helicoid. So a helicoid. Yeah, this is actually a very interesting example. Although it's not interesting yet. But let's acquaint ourselves with this example. Let's take a couple minutes to calculate it. It's worth having some experience with, because it is maybe one of the more interesting examples, period. Let's see here. I guess that was example 2. This is example 3 then. Example 3. And so this is the parameterization of the helicoid. And so what's a helicoid? Well, it's kind of like a helix, but what? Oh, you got it? Thank you. So if we, let's see here, if you fix u, right? It's basically the radius of a helix with slope 1. For this formula, like in Calc 3, we study helix. Helix is something like r cosine theta, r cosine t, r sine t, and then mt for the last, if you want to slope m helix. So if you think of v as being the parameter of the curve, fix u. If you fix u, you get a helix. Right? So if u varies, we get a whole family of helices, whatever they're called, whatever plural helix is. Helixes. On the other hand, what happens if I fix v? That puts us on z equals to a constant, right? And it's going in the cosine v, sine v direction, right? So that just traces out a horizontal line segment from the z-axis out to that. So like the helicoid is kind of like something like taking taking an infinite marker, I suppose, because it just goes on and on. Wait a minute, does it? Oh yeah, if u goes on, and just kind of like sweeping it out as you go up, that's a helicoid. I should be doing it levelly, but I should be doing it levelly. This is what mathematics is, or check it out. We got a book. There you go, picture right there. Anyway, so that's what it is. And he wants to do the pullback method, the pullback, so it's basically the same calculation we just did. Sorry for being boring, but he's going to pull back g bar, where g bar is dx squared, dy squared, dz squared. So it's the Euclidean metric on R3, yeah? And so you've just got, basically d of u cos v, you square that, and then plus the differential of u sine v, square that, and well then plus dv squared. And through a calculation very similar to the one we just did, I won't bore you with the details here, we get du squared plus u squared plus 1 dv squared. So that's actually kind of neat. It turns out that the cross terms in this one, when you FOIL it out, they cancel out. All right? So there's actually like a whole bunch of metrics like this. One popular kind of class of examples is if you look at like the half plane, you can do something like, well, here's another one, ds squared is equal to dx squared plus dy squared divided by y. That's, I think just by y is one. If this is for y positive, right? You can check that formula gives you a metric which is symmetric, and like the matrix of this. If you think of this as being G, well, the matrix of G with respect to like the Cartesian coordinates would just be like 1 over y, 0, 0. So it's clearly symmetric. It's clearly positive definite, provided we're in the upper half plane. So.
Did you use this example in complex?
Yeah.
When you do this thing?
Yeah. Yeah, we did more with this. But that's another example of a metric on a subset of the plane, which is not the Euclidean metric, right? And pretty much you could pretty much divide by any suitably reasonable function there, and you get all kinds of different metrics by choosing different what are called ruler functions. All right, enough. More on that later. Of course, another example of these calculations, which is also interesting, is we can look at like f of, let's see here, r and theta equals to r cos theta, r sine theta, right? And so like f is just a mapping, say from R2 to R2, something like that. And then if we pull back the, sorry to be so boring, let's pull back the G bar again. So we're looking at the pullback of dx squared plus dy squared once more. And so we're doing like d of r cosine theta plus d of r sine theta, and we're squaring those differentials. Let's do that. So that's cosine theta dr minus r sine theta d theta squared plus sine theta dr plus r cosine theta d theta squared. Keep in mind that those squares are shorthand for taking the tensor product of these one forms with themselves, right? The symmetric tensor product, which works out to cosine squared theta dr squared. Let's see here. See, I feel obligated to write it out since we're kind of at this point. Fine, I'll write it out. So that's cosine squared theta dr tensor dr minus r cosine theta sine theta dr tensor d theta minus r cosine theta sine theta d theta tensor dr, and then of course plus r squared sine squared theta d theta tensor d theta. That is all just from the first square. That's just from this, right? That's just expanding out the blue. And then the other one, I get myself a sine squared theta dr tensor dr plus r sine theta cosine theta dr tensor d theta minus r, or rather plus r cosine theta sine theta, however you want to write them, d theta tensor dr is my point though. And then plus r squared cosine squared theta d theta tensor d theta. I regret writing all this out. I should have written this out. This is more interesting. I'm a dummy. You know? Oh well. Although the details I didn't write out on the other one are in the book. But hey, these are in the book too. What am I doing? Sorry, I'm being boring. But you can see what happens is that the cross terms cancel, right? Like the mixed terms here, the dr d theta and the d theta dr, they're same terms, cancel, and they're just left with sine squared plus cosine squared. So we just get dr tensor dr plus r squared d theta tensor d theta, which we can more briefly write as dr squared plus r squared d theta squared. And so there you go. That's the formula. That's the formula for the Euclidean metric in polar coordinates, right? So if we have different coordinate systems on a given manifold, we can pull back the metric in one coordinate system to another coordinate system and find a different expression for the same metric on the manifold, just using different coordinate systems. This is another interesting calculation, because especially when you study differential Riemannian manifolds more deeply, you'll find out that there are certain special coordinate systems which reveal particularly nice features of the Riemannian metric. So you might want to look at that coordinate system to see more clearly what's going on. Like on the plane, if you're asking some question about the geometry of circles, maybe using the polar coordinate version of the Euclidean metric is better than using the Cartesian one. If you're asking a question about lines on the plane and the geometry of lines on the plane, probably this isn't the right thing to be looking at. Just saying. You guys you have been baptized by fire in this issue in Calculus 3, right? You know full well that if you choose the wrong choice of coordinates for doing a three-dimensional integral, you will pay the price, right? If you try to do a spherical problem using cylindricals or vice versa, and you will hit a brick wall very quickly. Yeah. Okay. Okay, so enough. I think I have shown you guys the pullback calculation enough. I think now you should be able to do some pullback calculations in the homework without much trouble, right? Like this is a pretty nice, I don't know, I think this is easy to understand personally, provided that you have a clear statement of the map that you're pulling back under, right? If you don't have a coordinate formula for it, if it's somehow described some other weird way, maybe it could be more tricky, but. So, next order of business, let's talk about the concept of isometry. Isometry, meaning same measure, right? So we've talked about diffeomorphism. So first of all, in topology, you guys have been talking about homeomorphism, right? No? Oh. Well, you should talk about homeomorphism. Homeomorphism, two topological spaces are homeomorphic, means that there's a one-to-one bijection, which is continuous with a continuous inverse. This means the two topological spaces are homeomorphic. Two topological spaces which are homeomorphic have the same topological structure. They're essentially the same topological space with just different notation. Just like in linear algebra, we learned vector spaces are isomorphic if essentially they have the same dimension. Two vector spaces being isomorphic really just says they're the same vector space, just using different notation. Now, I put same in scare quotes because when people say that, you know, a particularly weird object is the same as a totally different object, it bothers me. Like like a matrix is not a polynomial. They're not the same, but they do share the same linear structure, provided they have the same number of basis elements describing both. So to say two topological spaces are homeomorphic is to say that they have the same concept of openness and closedness and so forth. And essentially, a set will be open in the one topological space if and only if it is the image of an open set in the other one. So like the homeomorphism just maps open sets to open sets and closed sets to closed sets. It just transports the whole topological structure from one to the other. We say two smooth manifolds are diffeomorphic if they have essentially the same smooth structure, right? You can, go from one to the other and transport the concept of smoothness. Now we were talking about what does it mean for two Riemannian manifolds to be the same with respect to the Riemannian geometry. And so that's called a Riemannian isometry. So this is the definition. My point is that this is just the next chapter in that same idea. Trying to capture the sameness of two objects, trying to capture the concept that they have the same structure with respect to the structure we're talking about, which at the moment is Riemannian geometry. So here's the deal. If you have M paired with G, and another Riemannian manifold, M tilde paired with G tilde, all right? And these are isometric. Sorry, he's got the language all backwards for me. Isometric as Riemannian manifolds. If there exists a smooth diffeomorphism F from M to M tilde, such that what? What do you think?
Has to do with G.
Yep, has to do with G. So,
Oh, I
Mm-hmm.
Maybe something like if we went into our points.
Lazier.
Okay. G of 2 points.
Mm-mm. No.
G of
Not lazy enough. Not nearly lazy enough.
G does the same thing with G tilde.
No, this has something to do with what we've been doing all day.
Pullback.
That's right, pullback. So the pullback of what is what?
Okay, the pullback of G tilde is G.
Yeah, the pullback of G tilde is G. That's it. Yep.
Okay.
If there's a smooth diffeomorphism, which means it's a bijection which is smooth with smooth inverse, such that the metric in M tilde pulls back to the metric in M, that means that these are called isometric Riemannian manifolds. Now, oftentimes we're not, weirdly enough, we're often more interested not so much in global, I might call this global isometry. Sometimes we're interested in what's called local isometry. And by the way, this F like this is called a Riemannian isometry. Now, I think the things you're trying to tell me are exactly what would be true about F if we looked at it at a point.
Okay. And that's what we're going to do.
Yeah, we'll do that in a second here. A local diffeomorphism, right? So, here, F from M to M tilde, such that what? That's not quite how he has it. Let me use his precise language to keep myself out of trouble. He says F is called a local isometry. If every point P and M, right, has neighborhood U such that F restricted to U is an isometry of U to open subset of M tilde. Equivalently, well, he says, oh, fine, I would have been okay. Oh man, look at that, I would have been fine. I was well within my rights. The next sentence. Equivalently, if F is a local diffeomorphism satisfying F star G tilde equal to G tilde. Dang it, I could have saved myself a bunch of writing. So, F a local diffeomorphism with the pullback of G tilde equal to G is, that's also another way to define local isometry. Now he says this. He says, if there exists a Riemannian isometry between two Riemannian manifolds, we say that they're isometric as Riemannian manifolds. If each point in M has a neighborhood that is isometric to an open subset of the other, then we say that M is locally isomorphic to M tilde. And then he says the study of properties of Riemannian manifolds that are invariant under local or global isometries is Riemannian geometry. So, and then finally, Jeff, here we go. Or as some might say, let's go. Let's see here. Flatness. Flatness. A Riemannian manifold. Where was I? Good grief. M comma G is said to be flat. I'm sorry, I'll get it right eventually. A flat Riemannian manifold if M comma G is locally isometric to Rn with the Euclidean metric, or Rn Jabbar, as I've been calling it because I'm an idiot. The next exercise is to prove that if you have two isometric Riemannian manifolds, that one's flat if and only if the other is. In fact, it might not even be that. It might be, oh yeah, I thought it might be local, but anyway, yeah. Let's see here. Let's look at, because I think you're waiting for me to do this, and that's a reasonable request. Like, what does this condition actually mean? Right? Like, what does that actually mean? So if we talk about G of, say, VW, right? That would be F star G tilde of VW, right? But by definition, that's G tilde of what? Of F push forward V, F push forward W. If you'll allow me to use this notation here. Of course, we could put in points, and then we could talk about, we could do the dF sub P. But remember, dF sub P is the F lower star. Like, this is, if you like, dF star sub P is equal to dFP. I mean, depending on which book you look at, it may fuss more or less about the notation here in that regard. So this is what we, does this make sense? So if we calculate essentially the dot product between vectors v and w, then it's going to give us the same as the dot product on the isometric manifold between the push forward of v and the push forward of w. So this is the preservation of the dot product. It's analogous to like an orthogonal transformation in linear algebra. That, orthogonal transformation was the one you have like t of x dot t of y is what? X dot y, right? That makes t an orthogonal transformation. So this is the same kind of idea, But, well, anyway, it's not quite that. It's much more interesting, isn't it? But. So, natural question, how do you judge whether a given Riemannian manifold is a flat manifold? All right? So, here's a dumb one. Rn with the Euclidean metric is flat because it's isometric to itself under the identity map, right? Like, so there's one. Okay, not especially interesting example, but Euclidean space is flat. And in some sense, that's really the question, is like, when is a manifold and the geometry of the manifold the same as just the Euclidean geometry of the plane or extended n-dimensional space, right? So theorem, I'll be over here. Theorem 13.14 gives us a list of conditions that are, the following are equivalent for a Riemannian manifold. Okay? And I hinted last time, guys, that this is, these are answers, but there is a calculational scheme to decide this question more concretely, because these are all kinds of, well, you'll see, every one of these conditions is a little bit, it's indirect, all right? It's kind of indirect. These are kind of happenstance. Well, the first one's the definition. So there you go. G is flat. And by the way, we can either say that we can refer to the pair M comma G, or we could just refer to G. Oftentimes we just refer to G. Okay, so G is flat. It's a flat metric, as you could say. B, each point, P and M, there exists chart, right? There exists chart, xi, such that G is equal to Kronecker delta ij. Oh man, sorry. I'm trying to write sums in here, but he's free. He's, as you know, Lee has become a physicist. That's a year, and it's good. But I'm trying to write sums. So there it is. In other words, there exists a chart at each point such that you can put the metric into the Euclidean form. Okay? And then C, each point of M is contained in domain of a smooth coordinate chart in which the coordinate frame so that's this one, right, is orthonormal. That's dumb. I mean it's not dumb, but it's, goodness gracious, if that's not exactly the statement of B, I don't know. To me, it looks like the same statement. Maybe it doesn't look like it to you guys. But to say that it's orthonormal, we're talking about G orthonormal. What does that condition mean? G of partial xi, partial xj equals to what? Oh, well, but what is this? We defined this earlier. I mean, I reminded you guys earlier. We defined it last time. But remember, oh, I've erased it. Rats. So I said earlier that G orthonormal means that when you take the frame, you let the metric act on the frame, the ith one, the jth one, you just get Kronecker delta ij. That's right. But what have we talked about tensors? See, we've talked about tensors. We've said, oh, well, G is equal to the sum over I and j of Gij, dxi, dxj, right? But what is this? That's exactly Gij, right? That's how we calculate Gij in the x coordinate frame. So this is Gij, and so that's why I personally have trouble seeing the difference between statements A and B. But I guess that's good because that's kind of the point, isn't it? Is that they're equivalent, right? So I guess there you go. There's a proof that C implies B. There's a proof that C implies B. All right? And the proof that I think it goes both ways, actually, if you think about it for a minute. Because, right, I mean, it goes both ways, because to say that there's a chart that this happens, well, the meaning of these coefficients is these coefficients are exactly that by the interplay between tensor coefficients and how they're defined in terms of their action on the basis, right? So like, this proof goes both ways that I've just written on the board. And then, we got ourselves D. Ooh, look at this one here. Each point of M, is contained in domain of commuting orthonormal frame. Which does appear slightly different, right? All right. I'm going to resist the urge to prove that because I want to show you guys some more cool stuff today before we're done. So, oh, don't breathe this stuff, guys. Ever. Just don't do it. It's not worth it. So one important thing, which I probably inadvertently already used, if you really take a look at my earlier examples, I bet I've already used this idea. But we should state it formally, which is the induced geometry on submanifolds. So if we have S is a submanifold of M, with metric G, then of course we have S is included into M, perhaps, with that dreadful map. And so obviously if we take that dreadful map G, well then that should give us, does he have a notation for it? No, he just calls this the pullback metric on S. So, but this right here, this gives S the so-called, this is the induced metric. The induced metric from G. All right. And it's got a couple really cool examples here. I got an idea for another one. We'll see what happens, right? This might blow up in my face, but how about this for an example? Where was I? What example are we on? 6? Okay, cool. So, all right. How about this? You guys know this equation, the equation of this guy is what? X squared plus y squared equal to what? Let's say 1. Right? So, and of course this is the, let me call this S, right? S is a submanifold of R3, right? Okay. Can I pull back under the inclusion map G bar? That would look like what? That would look like, what would we have? We'd have, the pullback of dx squared plus dy squared plus dz squared, right? So the thing that makes this different at the moment is, how do you, what are coordinates on the cylinder? Any ideas? I mean, I guess we could do this. We could do z, we could do theta, right? We could parameterize this like x of, theta z equal to cos theta sine theta z. I wanted to do this without this, but we're running short on time, so I'm not going to fiddle around too much. So in other words, your x is this, your y is that, this of course is z, right? So what would that look like here? If I use that for my x, y, and z, I got what? I've got, d cosine theta, which is what? Minus sine theta, d theta, square that, plus what?